Okay, welcome back to the next week. Hopefully the midterm wasn't too horrible. If anything, you have fewer words to write because we had that 6,000 word limit in this class. You had some words to write on your midterm, so now you have fewer words to write in your other essays. So look forward to that. So the last things we were talking about were all the problems with social media, and then also we had a little bit of Python because there wasn't a second lecture because of the midterm. And then hopefully you got started on the essay and you did those anonymous evaluations. Okay, so let's move on now to evaluating and controlling technology. So how can we control it before it controls us, I guess? So we've got some downsides. How can we cope with them? How can we think critically about them? And I guess mostly is the best thing to do is to understand the ideas behind everything and how they can affect us. A little bit of history, a little bit of thought. Okay, so the first thing that you might have heard of is called Deepfake, and what it does is it takes an original video. This one is just a still frame from a video. This is an actual video that hopefully you're seeing, and well, it uses machine learning to swap faces. So suddenly you've got Nicolas Cage all over the place, and this is pretty insidious. This can get bad. All right, so we are used to this in still images, just photographs, because we have Photoshop. Everybody knows how to Photoshop somebody's face onto somebody else if they've ever learned the program. It's like the first thing you learn, right? The issue with video is, well, we use video to prove the guiltiness of somebody a lot of the time. So the second you can start doctoring, for example, security cameras to show whatever you want, maybe if you somehow get a hold of what was there, you can suddenly make it so that somebody who wasn't there was. Okay? So, for example, security cameras, or just I don't know, any video at all that anybody ever takes, you can prove that somebody was there now because you can deep fake them on to an existing person. And so obviously you can use this very easily for fraud, hoaxes, I don't know, everybody's really Nick Cage or something, and then for fun stuff too, of course. But there are some huge downsides to this, and it's something that we're going to have to live with as a society in the future. Suddenly, all our video evidence is not going to be as well trusted, and that is an issue. So if you're ever on a jury and somebody's like a hacker, make sure to consider that maybe something wrong might be happening with the videos. All right. The next thing that I want to talk about is Wikipedia. So we love it. We use it all the time. Anybody can edit it. Is that a bad thing? Should we just never use it now because anybody can edit Wikipedia? So people every day are adding / updating articles every single day. And so maybe the information that was on a page yesterday is not the same as the information that was on a page today. As it is today. And, well, Wikipedia does keep previous versions, so there's an old version of the page, and it saves it. And then there's the new version. Maybe they added another picture or added a few extra sentences. Well, is that a huge deal? Not really, is what you might say to the fact that it's changing. Well, news changes just as easily. So it's not a big deal. For example, when the wildfires were a thing, and they kind of still are, I guess. all of the news articles were updating themselves with like new evacuations, things like that. And a Wikipedia article is essentially the same thing. Like if you go to an article about a person, obviously they're going to do something new every day, and so maybe that's newsworthy. Maybe that's Wikipedia worthy. Okay? So that's one reason why maybe it's okay to use Wikipedia. The one big thing, and the thing that most people argue against, is about this word people. Who are these people? They're anybody. In particular, anybody, anyone can modify a Wikipedia article. I found a few typos once, and I actually did that. So it's not a huge deal, but maybe if you're a bad person, you can go and edit that article. And it might take some time. Eventually, somebody's going to come to the article that you just edited incorrectly and fix your problem, fix your lies. But there might be some time where those are still there. And I guess the idea is, well, does that mean you shouldn't use it? Going back to every teacher you've ever had probably saying that it's okay to use Wikipedia as long as you don't cite Wikipedia. You cite the sources that they use. So as long as you do your own research, I don't see the problem, and I hope you don't either, because at the end of the day, these people who edit the articles are always asked to include citations. You've probably seen this. Citation needed. All over the place. And this is key. If you ever see that, then you know that, oh no, maybe this isn't accurate. But otherwise, it's stood the test of time. So as long as you do your own research and actually visit the articles that are cited in Wikipedia, it's probably not the worst thing in the world. Again, I guess it just goes back to use good judgment and everything will be okay. But just keep in mind that your dog can edit Wikipedia, but as long as your dog cites good articles, that's not a problem. Okay, so that's Wikipedia. I assume that you knew most of that already, but just getting us all on the same page here. Some new cool thing that it would be fun to talk about is car crash tests. So you've probably seen some commercials. I remember they were back in the day, like show a picture of a car that's like in some kind of like warehouse where they're testing this vehicle, and they drive it into like a reinforced wall, and boop, here's the car. I don't know what a car looks like. I don't even know which angle I'm trying to draw it at, but that's not a big deal. This is a car, and it's going very fast into this wall. And that's a real-life car crash test, and you can imagine how expensive that is. To build the car that we were trying to figure out, hey, does it stand up well to crashes? A few, probably hundreds of thousands of dollars, because you don't have like the factory line ready for this brand new car, so you have to do it pretty manually. Drive that into a wall, and you just lost a whole lot of money testing this car. Okay, so most people, a lot of companies are going to simulate car crash tests in software before they even start thinking about building models, building real cars to drive into walls. Okay, so it costs a lot of money to run a car crash test in real life. Why not do it in software for free? So the idea is you can have all of this on a computer. I don't know if I can redraw this on a computer. Here's the little wall, here's the little car. I go that way. This is much cheaper. But the issue with that is it's not real life anymore. It would be nice if it were. And so if you're going to write a program, and you know how hard it is to write programs now, you have to model every little detail of real life inside of that computer, inside of that simulation. Okay? If you want an accurate test, you have to be precise. And I'm sure you know by now that it's very hard to do what you want in a program the first time. So it's probably impossible to be perfectly precise. We know a lot about physics. Like if you've taken a physics class, you've learned quite a few formulas, and those are all true. But we can't model all this stuff, like the exact alloy that the body of this car is made of. We can't model it down to the atom itself. Okay, that would take too much processing power that we just don't have right now. And so in software, when we're writing code to go and figure out how well this car is going to do when it crashes itself into a wall, all the software has to simplify a lot of stuff. And it's got to be like, okay, maybe I'll model every square inch of this car, and it's just a wireframe at that point. So it's just a bunch of like little boxes. Imagine like a Minecraft version of a car built of little tiny boxes that we can model. Okay, and that's the car. I'm not the best at drawing cars, as you can tell. But you can model those individual pieces maybe with accurate physics, but how do those hold up to actually real life and tiny little atoms? I guess the idea is this okay with you? Is it okay that the car companies are doing this when they're testing their cars? They're not actually running them into walls as often as you would like them to do. So one argument is, well, yeah, it's totally fine, because eventually they're going to perform a real car crash test. Eventually they're going to be like, okay, the software says this. I've tried all of these different things in software. This is the best one. Let's now go in real life and make the car and see if all the software was correct. And that's a good argument, I would say. But you can also make the following counter argument. You can be like, well, okay, maybe this car did well in software, but one of their other ones, the software was wrong, and one of their other ones would have done better. Okay, so maybe they could have picked a safer design if they did more real crash tests. That's the idea. So there's an interplay between these two things. How much money do you want to spend before you make your car? And how safe do you want it to be? And unfortunately, most car manufacturers are more interested in the money than wasting time making a bunch of cars to drive into walls. So I guess those are the two arguments, and you get to pick which one you are on the side of. So that's fun. Again, there's never a right answer, and I'm sure you know that by now in this class. So, okay, let's move on now. Let's talk about apps on your phone. So kind of like social media, but more about the operating system itself now. So Google can go into your phone and remotely delete an app that you had downloaded. Okay? Assuming it was from their store, that is. So Google has the power to remove stuff from your Android phone. Okay? And the idea is, well, in theory, they're only ever supposed to use this when they notice that somebody's installed a malicious application that got their way into the Google Play Store somehow, and enough people downloaded it for it to have been a problem, and they want to protect the users of their phones. So they're trying to protect you, so they're going to remove this app. But the problem is, once you allow for this kind of stuff, you have the authority, or you have the power to remove any app. So should they be allowed to do this is the first question. And I'm sure you can come up with good arguments on both sides again. You can say, well, yeah, they totally should, because I don't want my parents to have to worry about installing an app that was malicious and then it stays on their phone forever. I think Google should totally be allowed to get rid of that. But then on the other hand, you have the idea of, well, maybe one day a competitor to Google might come along and Google might make it very hard for them to do their stuff. They might start removing their apps from people's phones because they have that power. And obviously that's probably never going to happen. That would get them sued quite quickly, but that idea is still a possibility. Okay? So that's the idea there. And just to show you that this is not just Google, Apple has totally also done this. I couldn't figure out if they are still able to. That was up in the air for me. One other thing that Apple's done, as while we're on the subject, so you might have heard the news recently, they just took down the video game Fortnite from their App Store because they were protesting, the makers of Fortnite, they were protesting the fact that Apple requires a 30% cut of pretty much every in-app purchase. So that's a sizable amount, and they think that that's not a good idea. They think that's monopolistic, and so they are trying to challenge Apple in court. And so before they did that, in order for their suit to have merit, they made it so that they didn't give Apple that cut, and then Apple took them down, of course. So there are rules, I guess. There are rules to be on any kind of store. This is a more general idea. And if you don't follow them, you can be removed from users' phones as a developer. Your apps can be removed from users' phones or the App Store themselves, or the App Store itself. Okay. And then for everybody who likes irony, there was a time at which Amazon accidentally remotely removed copies of the book 1984, which I assume a lot of you are familiar with, from customers' Kindles. So that is some wonderful irony to get this lecture off started. So I guess the idea is the manufacturers of your devices might have a bit more control than you think that they do. And this is not to get you paranoid, it's just to get you thinking. Okay? So just keep that in mind when you make your next purchase. All right. So with that, let's move on to another thing that a manufacturer can do, a manufacturer of software can do on you. So forced upgrades is the idea of you have some version of software, like, I don't know, Windows 8. This was a thing back in the day, if you remember this. Windows 8 got replaced with Windows 10. And something that Microsoft did was have Windows 8 automatically install the newest version of Windows 10, which kind of messed up some people's workflows, and that always happens. So there were some programs that worked only on Windows 8, some new different things that happened on Windows 10 that people did not want to update, and they wouldn't have done them. They wouldn't have performed that update themselves were they given the chance. But Microsoft received a whole bunch of backlash for doing this. They took Windows 8 and they automatically upgraded it to Windows 10 for their users a lot of the time. So I guess the question is, do you have control over what's on your computer now? Because the manufacturer of your software might be able to upgrade your stuff for you. They could even take it away from you, for example, with DRM that we've talked about before. So what's the point of buying something if you don't have control over it, I guess? So the arguments for a forced upgrade is, well, there's a lot of things. And I think the best one, from my perspective at least, it's unfortunate that you can only get my perspective in this online class at the moment, but I really encourage you to think about your own. So an argument for a forced upgrade would be something like, okay, there are probably a ton of malicious things that people can do to old software, okay? Old software can much more easily be exploited, relatively. Oh no. There we go. Can easily be exploited. And so, I have no idea what happened, sorry. And so, it would be great for the manufacturer to automatically update for people, like install Windows updates, which you might be unhappy about, just to get rid of any potential vulnerability in your actual computer. So it'd be nice to prevent that. Okay, so that's probably the best argument I can think of for forced upgrades. And an argument against, of course, is you just lost control. And a lot of the time it's over software that they actually purchased themselves. So they spent good money for a particular version and it did everything that they wanted, and they did not want it to change. Okay? So you can maybe argue that this person is living in the past and they should move on, but there's a bit more of a gray area to that. There's a lot of the time some software changes drastically and somebody's work can't get done anymore. That's the idea. So force upgrades, a fun thing to think about, and I would love to have a debate again. I know I always say this, but I can't wait to get back in the classroom. Okay, one last thing to these set of slides before we start another, and then finish up this lecture, is equity. So just to make sure we're all on the same page, there's a big difference between equality and equity. So equity is when maybe some people get more, but that allows them to have the same experience. Okay? That's quite different from equality. And so the idea is, especially with this pandemic, is that you've got a lot of people, primarily from low-income households, who don't have the devices, that are getting force upgraded, that are getting their apps removed even. They're still beneficial. So a lot of people don't have these devices. They don't have an internet connection that's stable. They don't have a place to go with a computer that could help improve their lives. And that's a big deal, because if you don't have a phone, you can't get called for an interview. If you don't have an email address, you can't apply for an interview, things like that. And there's plenty more examples where that came from. And so I guess to close these slides, it's important to think about this. So how can we help these people? And I guess one thing that the college at least is doing is it's renting out laptops, it's renting out little MiFi routers, and I do encourage you, if you have any of those needs, to reach out to the college. I can help you with that. But this is something that's very important to think about, equity with respect to technology, because a lot of people don't have this kind of technology that we're talking about in this class. That's a real problem for their livelihoods. And so, yeah, just think about this from the point of view of the pandemic, especially. Most people are trying to go to school remotely, work remotely even, if possible. And I'm sure you've come across a class that might require Proctorio or something, just so that you can take a test, because it's probably easy in that class to cheat or something. Who knows? So there's no good answer to solve this problem, but there's a lot we can think about, I think. So that's where I want to leave us, and now I want to move on to the next set of slides, and then we'll just go through those a little bit. I think we're going to be a bit shifted now into every set of slides, but that's not a problem. We'll just keep going in order. Now I want to talk about risks and bugs. So this is applicable to your next short essay that's out right now. So let's start talking about errors, failures, and risks. Oh my. So I guess the question that we want to answer in this subsection is, how in the world, why are we still using computers when they have caused so many problems for us? They must be super nice to some people if they're still in use today. What's wrong? So what has gone wrong, I guess, is the first question. Okay, let's talk about this Ariane 5 rocket. And so it's just a series of rockets. There was probably Ariane 3, I know there was definitely an Ariane 4, And then the next version that they were coming up with, the European Space Agency, ESA, well, their next version, Ariane 5, had a bit of a problem. So it was a rocket. It was made by the European Space Agency, and the first time they tried to launch this new rocket, this brand new rocket, it ended up destroying itself because something went horribly wrong. So there was nobody on it, so that's not a problem. But why in the world did this happen? So after only 37 seconds into flight, it was like, nope, abort, we're done here, and it blows itself up. So this happened back in '96, and the cause was, believe it or not, software. A software bug. It wasn't like, oh, no, this engine stopped working. No, it was a software bug. It was not a bad one. It was a very subtle one too, and so that one little bug caused a loss of $370 million to this European Space Agency, and countless more money was probably lost in terms of people not trusting them to launch their satellites in orbit anymore, things like that. So that's really unfortunate. So let's talk about what went wrong, because this is a computer science class. What happened here? So the crux of the issue was that they tried to, I'm going to say these words and then I'm going to explain them. They tried to shove a 64-bit float, a number that was a floating point number with decimals, into a 16-bit int, so one that didn't have decimals. And this was normally okay. They didn't care about the decimals, that was fine. But they wanted to work with it as an int. And you actually know these words. You know every single one of them, but maybe not what they all mean together. Okay? So remember floats from Python. Float is like a cloud. Maybe I'll make this smaller. Float had things like 3.14, 5.67, all the numbers with decimal places. It still had 42, but it was more like 42.0. And then ints, coming from Python, those are your whole numbers. You can have negatives. You can have negatives up here, too. But they're all whole numbers, no decimal places, okay? Things like that. So the idea was they had a floating point number. They had a float, and they wanted to make it an int. And so they could do int things with it. It's a bit faster to work with ints in computers. Maybe that's why. That number represented something very important. So here is the first number. Let's just call it n. So they tried to take it. It was like, I don't know, some large number. I'll just use dots. It was 64 bits long, that number. And they tried to shrink it into a 16-bit version that had no decimal places. So this is a float, and this is an int, and it's 16 bits. So there's less information you can hold inside of a 16-bit number. That's the first thing that I want to show you. Like, a bit is just a 1 or a 0, and you can imagine that there's a ton more numbers that you can represent with 64 bits than you can represent with 16. Okay? So what this number that caused all these issues, what it represented was the horizontal velocity of the rocket. So let's pretend, I don't know the coordinate system that they were using, but let's pretend like here's the ground with the little launch pad, like, I don't know. Here's the Earth, maybe. How about that? And here's like, there's Europe. Whee! There's the UK. So here is their rocket. It's like it's shooting itself straight up. Boop, boop, boop. Like that. It's coming this way. Out. And maybe its horizontal velocity was like, they drew like a coordinate axis on the Earth. And like here was 0, 0. And here was like horizontal. Here is vertical. And then coming out at you, of course, is like the z-axis. Who knows? So like going towards, I don't know, going towards Asia was positive x for them, horizontal direction, and so horizontal velocity was some kind of number. Okay, so that's the number that caused all these issues, and the problem was it's what called it did it had what is known as an overflow. Those are the right words. Okay, and what that means is there was not enough room to store the number after conversion. Okay, that's what overflowing means. There wasn't enough room to store the converted number properly. And if you take CSCI 40, you might learn about something about this process of overflow and what might happen when that happens. So when overflow happens, either the number that was supposed to represent a large number, but we didn't have enough room for it, either becomes negative or it becomes very small. And that's just the way that overflow has problems. Okay, that's what overflow means. It's gonna make a different number that looks completely different from the number that it was supposed to be. All right, and so they never thought in the Ariane 4 that the horizontal velocity number would go this high and overflow, and they reused that code from the Ariane 4 in the Ariane 5, but the Ariane 5 went quite a bit faster than the Ariane 4 apparently, or it shot off it in a direction that was that hugged the ground a little bit more. So that just goes to show that a very small issue, and one that wasn't a problem before in a previous version of a rocket, can have drastic consequences. This is a small little bug, and that's why it was hard to catch it. Okay, well, that's really sad and unfortunate. They lost a lot of money because of a software bug. Oh no. Okay, let's talk about more problems. Voting systems, that's very... it's a good time for that, I guess. So there were a lot of issues in the past with voting systems. And the main issues were when people tried to use them electronically. So I'm talking about electronic voting systems. And I've never actually used one of these. I guess in California, it was only paper as long as I was a voter. So, or in the counties where I voted. So apparently, back in the day, or currently, some electronic voting systems, they just straight up crashed. And all the people waiting in line to go and vote, they just were out of luck. They couldn't go up to the machine because the machine wasn't working. Okay? And cast their little ballot with like a bunch of buttons. Who knows how that works. That's unfortunate. So some electronic voting systems, they just crashed, and so voters who wanted to vote couldn't vote. And once upon a time, a county lost quite a few votes, which, I mean, 4,000 might seem like not a lot, but that can change an election quite a lot, quite easily. And this happened because the machine's memory was full. So apparently, this voting machine was used by too many voters, maybe, because it didn't have enough memory to store all those votes. Or somebody like unplugged the cable. It was like maybe connected to the internet and was trying to give the information back to wherever it needed to go, but it couldn't. So it was trying to hold on to all the votes so that it could send them later. But oh man, it ran out of memory. So just 4,000 votes vanished into the air. That's really unfortunate. Okay, another thing. Oops. One county lost... another county in Texas. Now, there was a programming error, another bug, that generated extra votes. 100,000 extra votes. And it's nice to know that they caught that because we know about it now, but think of all the programming errors that might not have been caught and that caused extra votes like this. And that can totally sway an election. That sucks. Okay, one last one from the book. So this is probably the worst of programming errors. So a little bug that, it just caused, hey, you voted for one candidate? No, you really voted for another one. So you press one button and it votes for somebody that you didn't want to vote for. So this just goes to show you that it's probably best to do voting with paper, but I guess humans also have their own issues. it's hard to do this. It's hard to write software that's safe. And we'll talk about some ways to do it better, but I guess that's the moral right now. So, call your congressman. Make sure that you only have paper voting systems, for example. And just to show you that, I mean, maybe this is a US problem, who knows, but there are countries that are maybe better than we are at the moment in terms of safety for voting. Because in Estonia, and not to say that they didn't have problems when they first got this running, but Estonians can currently vote online. There have been studies to show that like the little username and password that they use can be hacked, but I mean, I guess somebody can also pretend to be you and vote before you or something like that. So there are problems when you vote, but some countries, they went all in for it. And I think that's probably going to be the future, so maybe we should look out for that. Okay, so that is voting problems. And now let's get on to a topic that you're reading about currently. So this is what your essay is going to be on, so we'll talk about it a little bit now, and maybe it might help you a little bit if you're watching this before it's due. So the Therac 25, I assume that's how you pronounce it, I'm really not sure. It was a radiation therapy machine. And so, for example, if you have cancer, maybe it would shine some very, very focused radiation at the spot where the cancer was, and hopefully help cure it. So this was made by a company, and it comes from a long line of Therac machines. So there was like a Therac 5, a Therac 20, if I remember correctly. Those all existed, and now they're like, all right, the new cool thing is Therac 25. And this was the first one that had software doing everything, okay? So it was first made in 1982, and the first documented accident happened in 1985, but that doesn't mean that there weren't accidents before this, because we're going to talk about what was wrong, and those issues definitely probably were there when it started out. So the errors in the code and the errors in the design ended up giving some people about 100 times the amount of radiation they were supposed to get, and just people weren't trusting them when they said that they came out of this machine and they felt like they were being burned, okay? They're like, no, that couldn't have happened. Or they're like, oh, you don't know what you're talking about. That's what it was supposed to feel like or something. Who knows? The problem was the software. And the reason that even if they reused the software from before, the reason that they didn't get issues before on previous versions of this Therac machine is that there were hardware systems in place to block excess radiation. So regardless of what the software said, if this little mechanical place is not over this other one, you're not having any radiation being emitted. It's not happening. There was a hardware fail-safe in those previous machines. Okay? And even if there was a software error, the hardware would fix it. Okay? It would make sure that nobody's getting hurt. Okay? So the problem with the software, though, is if you're trying to test for all this stuff, and you're assuming that the software was okay because it wasn't a problem before, that doesn't mean that it's not wrong still. There's a whole big can of worms that opens now, and I guess the first thing to talk about is it the programmer's fault when people get hurt? And so let me talk to you a little bit about how software gets made, because it's going to be very hard to assign blame. So usually, people are working together. Like, there wasn't just one person programming this machine, of course. Usually people are working in very large teams, and they're working on very small portions of software, and they might not know the big picture. It is possible. like how their small portion that they're working on fits into the large machine. And so maybe one of the programmers thought that, somebody else's code was going to fix any potential problem, and that wasn't the case. So I've said this now before, but you know how easy it is to make a program that's supposed to do one thing but does a completely different thing. And the future isn't super bleak. There are still going to be issues all the time, but there is a way out of this problem, at least to an extent. And the answer is testing and verification. Okay? So those are our only hope in the face of these issues that we've been talking about. So how can we fix the Therac 25? How should it have been developed? Well, there should have been more testing. There should have been more verification. And these words might actually seem like they're the same thing, but in computer science they are not. Who knows why? Okay, I think in the last couple minutes, let's talk about testing really quick. So testing is one of the easiest ways to catch bugs. And I would really encourage you to test your code if you're not already. If you're just like clicking the start button and praying that it's going to work, that will not work forever. Testing is much better of an idea to use. Okay, so it's one of the easiest ways to catch bugs, which is super nice. And but it doesn't catch them all. So that's one issue. Unless you have really, really good tests, and it's also often impossible to write perfect tests. Okay? And the one issue, at least I've discovered in my teaching, and this is also a thing that everybody talks about in industry, most people hate writing tests, which is really sad, which means that you're going to have more of these issues if you don't change something fundamentally about the way people view tests. So let's quickly write a program and a test. So I'm not going to pull up Scratch or Python or anything. Let's just do it ourselves. Let's pretend that we made a multiply the numbers from 1 to n block. So I can put like a number in here, like the number that the user entered, and that will be our block. And let's imagine how we might have implemented it. Okay? So it'll be like, okay, maybe I'll start a counter. I'll set my counter. My counter's count to n. And then I'll start another variable, and I'll set it to 1, and that will be my result. I'll start it at 1 so that I can keep on multiplying into result by count. And so I'll start count at n, I'll multiply result by n, so now result is now n, and I'll decrement count. Count can now be n minus 1, and I'll keep doing this process, multiply at n as long as count is bigger than 1. Okay, so now it's that, then I'll multiply it by, it's not n anymore, I'll multiply that by n minus 1, and now I'll subtract 1 from count, and I'll keep doing this process. I think you can understand how you might make a program that does this. I'll be like, all right, now it's times n minus 2, now it's n minus 3, and this goes on forever, dot, 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 until you multiply by 1, and count is 1. And now the second that you make count 0, it's like, okay, I can stop now. This is my final answer. It's in result. Okay, so that can be our program. I encourage you to try and write it, but let's now write a test, okay? And, oops. One of the things that you should be doing when you write tests is think about what are known as the corner cases. And that's where are almost correct, but not quite. You should also think about the incorrect cases. Or where the program is about to do something different, to change and do something different. and I'll tell you what that means in just a second. Also think about the incorrect cases. Okay, what is a corner case? That's something where you're about to like give back the answer. Like let's make count 1 and see what happens there, because that stops this entire loop thing that does stuff to result, right? So a nice corner case would be where count is 1, n is 1, n is 0. What happens there? Maybe n is 2. So around these cases where things change, where our program changes the way it executes. Okay, because something is supposed to happen when count is either 0 or 1, depending on your program. So we should test everything around there. Okay, so those are corner cases. And then incorrect cases are things like, all right, what happens when we increment, when we put in, I don't know, negative 42 here? What happens? And then see if your program does what you expect. Maybe you should have an error case, like tell the user, no, what you're doing is wrong. You should never enter a negative number. And then another test could be just normal numbers. Like n equals 5. N equals 8. That should be enough to check the general case. And what a test is you compare what you got with what you expected. Okay? And so a test is, okay, I gave n equals 5, and I expected if if n started out being 5, I must have gotten back 5 times 4 times 3 times 2 times 1. I'm going to do the math and make sure that I see this answer. That is a test. Okay? It's pretty self-explanatory, but you can write a program that does this for you. Okay? And that's where I want to leave us. So now you know how you might write a program that you have some confidence in. So I encourage you to maybe write a few programs and think about how you might test them, or test some programs that you've already written, or that I've given as an example in class. Okay, so that's a good place to stop, and so I'll see you next time now.